What derivatives tell us about the shape of a graph? First, let's look at the increasing-decreasing test. If the derivative of a function is positive on an interval, then that function is increasing on that interval. And if a derivative of a function is negative on an interval, then the function is decreasing on that interval. This result is not too surprising. If you look at the graph here, you can see clearly the function is increasing from point A to point B. And if you imagine drawing any tangent line to the function in between these 2 points, the slope of that tangent line would be a positive number, and that means the derivative would be positive. But from point B to point C, the function is clearly decreasing, and if you were to draw any tangent line to any point in between these 2 points, the slope of that tangent line would clearly be negative, which means the derivative would be negative. Let's take a look at an example. Here we want to determine where the function is increasing and where it is decreasing. So the first thing we do is we take the derivative of our function. So here the derivative f prime of x is going to be 3x squared minus 12x minus 135. And if I want to know where the derivative is positive or negative, the first thing I need to know is where does the derivative equal 0. So I'm going to solve this by factoring. We can factor out a 3 from each term. And then we can go ahead and continue factoring using 9 and 5. And we can see clearly the values of x that make the derivative 0 are positive 9 and negative 5. And remember, the number here does not produce a solution to the equation. Now this is where the derivative is equal to 0. So to figure out where the derivative is positive or negative, I will draw a number line, put these 2 numbers on that number line, and then we are going to test the derivative on each of the intervals between these numbers, or to the left and right of these numbers. So for a number that is less than negative 5, I need to choose any representative, and I will choose negative 8. For a number in between negative 5 and 9, I will choose 0. And for a number to the right of positive 9, I will choose 12. Now we're simply going to plug each of these numbers, these test numbers, into our derivative. And I recommend you plug it into the factored form because it is easier. So for example, if we use the test value x equals negative 8, we want to know what is f prime of negative 8. Well, if you plug negative 8 into your derivative, you get 3 times negative 17 times negative 3. And we know this number is positive because a negative times a negative is always a positive. So on this interval, the derivative is clearly positive. Now I do the same thing with my next test number, which is x equals 0. So f prime of 0 will be 3 times 0 minus 9 times 0 plus 5, which is 3 times negative 9 times 5. And this is clearly negative because when you multiply 3 numbers, if one of those numbers is negative, it gives a negative result. And finally, when x equals 12, f prime of 12 will be 3 times 12 minus 9 times 12 plus 5, which is 3 times 3 times 17, and this is once again clearly positive. And so what this means is that the derivative is positive for all numbers less than negative 5, and it's also positive for all numbers greater than positive 9. And the derivative is negative between these 2 numbers. And now we can directly translate that to where the function f is increasing or decreasing. So f of x is increasing whenever the derivative is positive. And so that is going to be on this interval here and this interval here, which we can write as the interval from negative infinity to negative 5, union the interval from 9 to infinity, and f of x is decreasing on the other part of the number line, which is between the numbers negative 5 and positive 9. Now this is a pretty simple example because our original function was a polynomial and the derivative of a polynomial is also a polynomial. And it's fairly easy to solve polynomial equations and test, but for other functions it could be a little bit more challenging. Now let's talk about local maximums and minimums. The first derivative test says suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum at c. If f prime changes from negative to positive at c, then f has a local minimum at c. And if f prime is positive to the left and right, or negative to the left and right of c, in other words, it does not change at c, then there is no local maximum or minimum at c. And here we have some diagrams to help us understand this. So here we have a function where you can see it is increasing, so the derivative is positive, and then it's decreasing, so the derivative becomes negative. So if first the derivative is positive and then it changes to negative, you must have a local maximum at that point. If it's decreasing and then increasing, then you'll have a local minimum at that point. However, if the function is increasing and then continues to increase, you have no local maximum nor a local minimum. And the same is true if it's decreasing and then continues to decrease. So this is the first derivative test. Now let's apply this test to the first example. So here we want to find the local minimum and maximum values of the function in example number 1. So here is that function. Let's go ahead and bring in our number line. So here is that number line that we got for the first example. We know the first derivative is positive here and then changes to negative. So that means that at this number here, negative 5, we should have a local maximum according to our first derivative test. So we're going to say f of negative 5, which is negative 5 to the third power minus 6 times negative 5 squared minus 135 times negative 5, which ends up being 400. This is a local maximum. Likewise, at x equals positive 9, the derivative changed from negative to positive, which means the function was decreasing and then increasing. And that means we have a local minimum there. So f of 9, which is 9 to the third power minus 6 times 9 squared minus 135 times 9, which is negative 972, this is a local minimum according to the first derivative test. And let's go ahead and bring in a graph to see what that looks like. So here is a graph of that function. We can see that the function was increasing, and then at x equals 5, it changes to decreasing. And then at x equals 9, it changes to increasing again. And here is our local maximum, the point negative 5, 400. And here's our local minimum, positive 9, negative 972. Now let's do an example that is not a polynomial. So here we want to find the local maximum and minimum values of the function g of x equals x plus 2 times the sine of x on the interval from 0 to 2 pi. So like before, the first thing I'm going to do here is take the derivative of this function. And the derivative is 1 plus 2 times the cosine of x. And then we set that derivative equal to 0. And in doing so, to solve this equation, I can subtract 1 from both sides. And then I can divide by 2 on both sides. And we see that cosine of x must be negative 1/2 for the derivative to equal 0. So now we need to think about, where does cosine equal negative 1/2? Now there are a lot of ways to solve this. For me personally, I like to think about quadrants. So if cosine is negative, we know that that happens in the second quadrant and also in the third quadrant. And I like to make a little reference triangle here. And cosine we know is the adjacent side over the hypotenuse. So I will emphasize that or represent that by putting negative 1 over positive 2 in both triangles. And that means the missing side here is radical 3 and negative radical 3, because we should recognize that this is a 30, 60, 90 triangle. Furthermore, we know that this angle here is 60 degrees, as is this angle here, which means my two angles in degrees are 120 degrees and 240 degrees. But of course, in calculus, we don't use degrees, we use radians. So, all that to say, the two values of x between 0 and 2 pi that give you a cosine value of negative 1/2 are 2 pi over 3 and 4 pi over 3. Now, of course, there are other ways to do this. You can use the unit circle, etc. I just thought I would put a real quick way to think about this. Now let's get back to our problem. So now I'm going to draw a number line, and this time it's going to be a finite number line because we only care about values of x between 0 and 2 pi. 2 pi over 3 is a value, let's say, here, and 4 pi over 3 is a value here. And then we need to test to see if our derivative, g prime of x, is positive or negative on each one of these intervals. So I need to think of angles that I can choose that are in these intervals that are easy to plug into my derivative function. So the angles that I'm going to use are going to be pi over 2 for an angle between 0 and 2 pi over 3. And then I'll choose x equals pi for the next angle. And then 3 pi over 2 for the last angle. So I like using quadrantal angles if I can, because they are usually a little bit easier to plug in. And now we're going to test each of these. So g prime of pi over 2 is 1 plus 2 times the cosine of pi over 2. And we know that cosine of pi over 2, is 0. So g prime of pi over 2 is 1 plus 0, which is 1, and that is positive. And that means our derivative is positive here. Then we do the same thing for pi. F of pi is 1 plus 2 times the cosine of pi, which is 1 plus 2 times cosine of pi is negative 1. And this gives us negative 1 as an answer, which is clearly negative. And finally, we plug in 3 pi over 2 into our derivative. Here, this should be g prime. We get used to using f. Okay, here we go. Plug 3 pi over 2 in, we get 1 plus 2 times the cosine of 3 pi over 2. And the cosine of 3 pi over 2 is also 0, and so we get 1 again, which is positive. So that means our function has a positive derivative here, a positive derivative here, and it has a negative derivative here. But in this case, they aren't asking us for increasing and decreasing. They're only asking us for the local maximum and minimum values. So we just need to apply the first derivative test that says if a function is increasing and then decreasing, we should have a local maximum here. So g of 2 pi over 3 is going to be our local maximum. All we have to do now is plug it into the original function, which is this function here. So that's going to be 2 pi over 3 plus 2 times the sine of 2 pi over 3. And I won't get into the details on this one, but this is 2 pi over 3 plus 2 times the sine of 2 pi over 3 is radical 3 over 2. And so this is 2 pi over 3 plus radical 3. And again, this is our local maximum. And then when we plug in 4 pi over 3, this will be our local minimum because the function changes from decreasing to increasing at this value. So when we plug 4 pi over 3 into our original function, we will get this. And when we evaluate it, we get 4 pi over 3 plus 2 times negative radical 3 over 2. And this ends up being 4 pi over 3 minus radical 3. And this is our local minimum. And we'll bring in a graph just for confirmation. Okay, so you can see here the function is increasing from 0 to 2 pi over 3. And then it's decreasing from 2 pi over 3 to 4 pi over 3. And then increasing after that. And therefore we have a local maximum at this point right here. Now this point is the approximation of this y value. And we have a local minimum here. And this point gives a approximate value for the y value here. Now let's talk about concavity. If the graph of f lies above all of its tangents on an interval, then f is called concave upward on that interval. And if the graph of f lies below all of its tangents on an interval, then f is called concave downward. So let's bring in a graph just to help us understand this. So you can see in the first graph, the tangent lines are below the graph. So the graph lies above its tangent lines. And we call this concave upward. So to think of concave upward, if I were to continue this shape, you would think that the concavity is in this direction. Think of it as it would hold water, right? So we could put water in here. That's what concave upward means. And if the graph lies below all of its tangents, then it's concave downward. So if we were to continue the graph in this manner, it is the case here that the graph would not hold water, right? The water would dump out here. And that's what it means to be concave downward from an intuitive perspective. But this is difficult to actually think about in terms of determining if a graph is concave upward or downward. So instead we have what's called a concavity test, and it's very simple. If the second derivative of a function is positive, then the graph is concave upward on that interval. And if the second derivative of the function is negative, then the graph is concave downward on that interval. And if a graph changes concavity at a point, so it changes from concave up to concave down, for example, then that point where it changes is called an inflection point. So let's take a look at this example. Here we want to find the intervals on which this function f is concave upward or concave downward. And then we also want to find the inflection points. So it all starts with taking the first derivative. So f prime of x here is going to be 6x squared minus 18x plus 12. Now let's keep in mind that the first derivative tells us about increasing and decreasing and maximums and minimums. But we are not asking about that here. We are asking about where is it concave upward and concave downward. So we need the second derivative. The second derivative is 12x minus 18. And now we're going to set that second derivative equal to 0, and then solve for x, which will be 18 divided by 12 in this case, which is 3 over 2. And then just like before, I'm going to draw a number line, but this time the number line represents the second derivative, not the first derivative. And it only has a single number at which the second derivative is 0. And then we will just test a number to the left of 3/2, so I'll use 0 there, and a number to the right of 3/2, I'll use 6. And then we simply plug those numbers into the second derivative. So f double prime of 0 is 12 times 0 minus 18, which is negative 18, which is clearly negative. And if I plug 6 into the second derivative, we get 12 times 6 minus 18, and this is 72 minus 18, which is 54, which is clearly positive. Okay, so we know the second derivative is positive to the right of 3/2 and negative to the left of 3/2. And for the second derivative, remember, where it's negative is where it's concave down, and where it's positive is where it's concave up. So the intervals of concavity, we will just say it is concave up or upward on the interval from 3/2 to infinity, and it is concave downward on the interval from negative infinity up to 3/2. Furthermore, we do have an inflection point, because since it changes from being concave down to concave up at 3/2, that point on the graph is an inflection point. So to get the inflection point, we have to plug 3/2 into the original function. So f of 3/2 will be 2 times 3/2 to the third power minus 9 times 3/2 to the second power plus 12 times 3/2 minus 3. And let's go ahead and compute this by hand. Why not? So we have 2 times 27 over 8 minus 9 times 9 over 4 plus 12 times 3 over 2 minus 3. And then we could do a little canceling. So 2 goes into 8 4 times. Here, 2 goes into 12 6 times. And the simplification here is 27 over 4 minus 9 times 9 here is 81 over 4, plus we have 6 times 3 is 18, and then minus 3. And 27 take away 81 is negative 54 over 4. And then plus 18 minus 3 is 15. And this is negative 27 over 2 plus 15. I can write over 1, and that means it's the same as 30 over 2, which would be 3 over 2, which is interesting. So f of 3/2, which is also 3/2, is our inflection point. Okay, and so that is the point on the graph where it changes concavity, and then here are the intervals where it is concave upward and concave downward. In this next example, we are going to put it all together. We have a function here, and we want to find the intervals of increasing and decreasing, local maximums and minimums, intervals of concavity, and also inflection points. So when you're doing everything, what I recommend is that you sort of divide this into 2 parts. So on one side here, I'm going to do everything related to the first derivative, and on the other side, I'm going to do everything related to the second derivative. So let's go ahead and compute the first derivative. We need to use the product rule. We have 2 functions here. So that first derivative is going to be x squared multiplied by the derivative of natural log of x, which is 1 over x, plus then the derivative of x squared, which is 2x, times natural log of x, So our first derivative here is x plus 2x natural log of x. Now for our second derivative, we are going to take the derivative of this function. Derivative of x clearly is 1, plus, and then the derivative here will be a product rule once again. So we will have 2x multiplied by the derivative of natural log, which is 1 over x, plus the derivative of 2x, which is 2, times the natural log of x. And this is, after you cancel the x's here, we're going to have 1 plus 2, which is 3 plus 2 times the natural log of x. And that is our second derivative. Now, to find the intervals of increasing and decreasing, we are going to set our first derivative equal to 0. And we're going to solve this equation by first factoring out an x, which is going to give us 1 plus 2 times the natural log of x. And then we're going to set each of these equal to 0. Now here we get x equals 0. For the other one, we get natural log of x is equal to negative 1 divided by 2, right? So I'm just subtracting 1 and then dividing by 2 there. And then we know that e to the natural log of x would have to be equal to e to the negative 1/2. These cancel out, and so we get x is equal to e to the negative 1/2, or 1 over e to the 1/2, which you can also write as 1 over the square root of e. Okay, so these are our critical numbers, right? Well, not exactly. So we need to remember that when you have a function, your function a lot of times will come with its own domain. And you know that you cannot take a logarithm of 0 and you cannot take a logarithm of negative numbers. So the domain of this function to begin with is only positive numbers, which means x equals 0 cannot be a critical number. Okay, so this is our only critical number. Now let's go ahead and set the second derivative equal to 0 as well, and let's solve that equation. So natural log of x here is going to be negative 3 divided by 2, and then e to that thing and e to that thing must be the same, and so we get x is equal to e to the negative 3/2, or 1 over e to the 3/2. Okay, now this isn't called a critical number, but it's an important number because we're going to use it to determine where it's concave up and where it's concave down. All right, now let's go back to part A. So for part A, I'm going to draw a number line. And this number line is really just going to be array, and it's going to start at 0. And then 1 divided by the square root of e is somewhere over here. It's a positive number. And I'm going to test both sides of that number in the first derivative. So what is 1 divided by the square root of e? Well, it's 1 divided by 1 point something. So we just need a number less than that. And a number less than that, I think it's pretty clear, would be a number like 1/10. And a number greater than that, we can pick lots of numbers, but I'll just pick x equals 5. And then I'm going to plug 1/10 into my derivative, and I'm going to plug 5 into my derivative. So my derivative is right here. When I plug in 1/10, I get 1/10 times 1 plus 2 times the natural log of 1/10. And all I care about is whether this is positive or negative. And this is not an obvious thing here. Okay, so in some instances like this, it's going to be really convenient to use a calculator. But if you plug this into a calculator, I'll just tell you, you're going to get a negative value here. Okay, so this is going to be less than 0. And then when you plug in 5, you will get 5 times 1 plus 2 times the natural log of 5. This is clearly going to be positive. And this is because these are all positive numbers and they're all added together and multiplied together. So that's going to be a positive. So the derivative is negative here and positive here, which means it is decreasing on the interval from 0 to 1 over the square root of e, and it is increasing on the interval from 1 over the square root of e to infinity. So this is part A. Part B, what are the local maximums and minimums? Well, there's only one. It goes from decreasing to increasing. So we have a local minimum here. So f of 1 over the square root of e is our local minimum, but what is that value? Well, we have to plug it into our original function, which was x squared natural log of x. So that's going to be 1 over the square root of e squared times the natural log of 1 over the square root of e. This is going to be 1 over e, and then this is the natural log of 1 over e to the 1/2. Or I can write this as the natural log of e to the negative 1/2. And what happens here is these cancel out, and you just get 1 over e times negative 1/2, and that gives us a final result of negative 1 over 2e. And again, this is our local minimum. Okay? So again, I think when you do an example like this, you really gain an appreciation for the polynomial examples, because polynomials are much simpler to deal with than logarithmic functions and other types of functions. Now let's talk about concavity. So we'll go back up to our second derivative. I'm going to draw a number line for that. Again, our number line is going to start at 0, and the only number on there is 1 over e to the 3/2. And we're going to test two numbers. So again, the number to the right, I'll just pick 5. And to get a number to the left here, I will pick 1/10. That also works again. And we're going to plug these numbers into our second derivative, which is this function. So we have 3 plus 2 natural log of 1/10 and 3 plus 2 natural log of 5. The second one is clearly positive. And then this one is not clearly positive or negative. So again, a calculator here will really help, but I will just tell you that this value is negative. So it's less than 0. So second derivative is negative here. It is positive here. So that means it is concave down on the interval from 0 to 1 over e to the 3/2, and it is concave up on the interval from 1 over e to the 3/2 to infinity. And at this number, we have an inflection point. So f of 1 over e to the 3/2, which is going to be 1 over e to the 3/2 squared times the natural log of 1 over e to the 3/2. And this is going to be 1 over, when you square this, you're going to multiply those powers, so that's going to become e cubed. And then the natural log here, you can rewrite this as the natural log of e to the negative 3/2. And so that cancels, and you just get times negative 3/2. And so this is negative 3 over 2e cubed. And this is our inflection point. So once again, numbers here are not our favorite numbers, I'm pretty sure. And we gain an appreciation for the simpler examples by doing a more complicated one like this. And here is a graph of that function. So I just want you to notice that we do have a local minimum at this point, and it's really hard to see, but the function is concave down, so there's a very slight curvature this way here. So right here it is concave down, and then somewhere right in here it changes to concave up. And that point right there where it changes is our inflection point. Okay, so that is this point right here. Okay? All right. In the next example, we are going to do the same thing for the function f of x equals cosine squared of x minus 2 times the sine of x on the interval from 0 to 2 pi. So again, I like to divide my work into two parts. I'm going to talk about the first derivative here and the second derivative over here, just to kind of keep those things straight. Let's go ahead and take the first derivative. So remember, when you have cosine of x squared, that is the same as cosine squared of x. The derivative is going to be 2 cosine x to the 1 times negative sine of x. So when I take my derivative of this, I'm going to get negative 2 sine of x cosine of x, and then minus 2 times the derivative of sine, which is just cosine. Okay, so that's not too bad. Now the second derivative, I need to take the derivative of this. So let me take the negative 2 out, and then I'm going to view these two functions as a product. So the derivative is going to be the first function sine times the derivative of the second function. Derivative of cosine is negative sine. And then plus the derivative of the first function, which is cosine, times the second function, which is cosine. And then we have minus 2 times the derivative of cosine, which is negative sine. So be very careful with all of your positives and negatives here. But in the end, I have negative sine squared here multiplied by negative 2 will be positive 2 sine squared. And then cosine times cosine is cosine squared times negative 2 is negative 2 cosine squared. And then we have plus 2 sine of x. Okay, so here is our second derivative, and here is our first derivative. Now, let's talk about the first derivative. We are going to set that derivative equal to 0, and I can factor out a negative 2. I can factor out a cosine, and what's left is sine of x plus 1. And then we will set this equal to 0, cosine of x equals 0, and we'll set this one equal to 0, which of course means that sine of x is negative 1. And then we need to know, where do these happen between 0 and 2 pi? Now, we should know these because these are really basic values here, but cosine is 0 at pi over 2 and 3 pi over 2, and sine is negative 1 at 3 pi over 2. So these are our critical numbers. Notice that 3 pi over 2 is listed twice. That's okay. We only need it once. Remember, our original interval is from 0 to 2 pi. And then we're going to put pi over 2 on this line and 3 pi over 2 on this line. And then we're going to test our first derivative to see if it is positive or negative on each of these intervals. And to do this, you have to pick a test point. So here I will choose pi over 6. Here I will choose pi. And over here I will choose 11 pi over 6. And I have to plug all these into our first derivative. So f prime of pi over 6 is going to be, you got to plug it in either here or here. I think I'll do the second one. So I have negative 2 cosine of pi over 6, and then sine of pi over 6 plus 1. And this is negative 2 times the square root of 3 over 2 times 1/2 plus 1. And remember, we only care if it's positive or negative, and this is negative because we have a negative here and everything else is positive. Then we're going to plug in pi, so f prime of pi will be negative 2 cosine of pi times the sine of pi plus 1, which is negative 2 times negative 1 times sine of pi is 0, so we get 1 there, and this is positive. So the first derivative was negative here. It is positive here. And finally, let's plug in 11 pi over 6. So we have negative 2 cosine of 11 pi over 6 times the sine of 11 pi over 6 plus 1. This is negative 2. Now the cosine of 11 pi over 6 is radical 3 over 2. And the sine of 11 pi over 6 is negative 1/2. Okay, so what do we have here? We have a negative number here, and this is a positive number here. So this is going to be a negative. So the first derivative is negative there. So what do we know? Well, we now know that the function f of x is increasing on the interval from pi over 2 to 3 pi over 2, right? Because it's increasing when the derivative is positive, which is in here. And then it is decreasing on the other two intervals, this interval here and this interval here. So we'll say it is decreasing on the interval from 0 to pi over 2, union, right, also 3 pi over 2 to 2 pi. Furthermore, we know we have a local minimum here and a local maximum here. So f of pi over 2 is a local minimum, and f of 3 pi over 2 is a local maximum, and we got to plug those back into our original function, which is this function right here. So we have cosine squared of pi over 2 minus 2 times the sine of pi over 2. This is going to be 0 minus 2 times 1, which is negative 2. And then cosine squared of 3 pi over 2 minus 2 times the sine of 3 pi over 2 is 0 minus 2 times negative 1, which is positive 2. So f of pi over 2 is negative 2. This is a local minimum. And f of 3 pi over 2, which is positive 2, is a local maximum. So we've got parts A and B answered. Now let's take a look at part C. So to figure out concavity, we have to take the second derivative now and set it equal to 0. All right, but solving this equation is tough because we have different trig functions. So what I'm going to do here is I'm going to change cosine squared to be 1 minus sine squared. That is a Pythagorean identity. So we get 2 sine squared of x minus 2 times 1 minus sine squared of x plus 2 sine of x equals 0. This is 2 sine squared of x minus 2 plus 2 sine squared of x plus 2 sine of x equals 0. And this is 4 sine squared of x plus 2 sine of x minus 2 equals 0. And now we're going to factor. We can pull out a 2. And then we can further factor this into the following. And then we're going to set each of these factors equal to 0. So 2 sine of x minus 1 equals 0, and sine of x plus 1 equals 0. And here we get sine of x equals 1/2, and here we get sine of x equals negative 1. And so the values where sine is 1/2 is going to be pi over 6 and 5 pi over 6. And the value where sine is negative 1 is 3 pi over 2. And we do the same thing. We set up our number line. This number line represents the second derivative. And we're going to put pi over 6 on this number line, 5 pi over 6 on this number line, and 3 pi over 2. And we have to test values in between these values. And this is where it can get a little bit tricky, because when you have a value like pi over 6, What is a value less than pi over 6 that you know? Well, there are no special angles. So I'm just going to use something like pi over 12, okay? In between the next two, I'll use pi over 2, and then I'll use pi, and then for the last one, I'll use 11 pi over 6 once again. And you're going to plug these into your second derivative. So that second derivative is right here. And I'll just do the first one. And then for the rest, I'm just going to write down the results. So for the first one, we have 2 times 2 sine of pi over 12 minus 1. And then sine of pi over 12 minus 1. And I just want to know, is this positive or is this negative? And excuse me, this is plus 1 on the last part there. There we go. Well, sine of pi over 12 is a positive number because it's in the first quadrant. Plus 1 is a positive number. This is also a positive number, so the only question is whether this is positive or negative. Well, sine of pi over 6 is 1/2. Sine of pi over 12 is less than 1/2. So 2 times a number less than 1/2 is a number less than 1. And when you subtract 1, that will be a negative number. So this is going to be negative. Now for the rest of these, I'll just fill them in. And let's go ahead and walk through them. Sine of pi over 2 is 1, times 2 is 2, take away 1 is 1. And here we have 1 plus 1. So those are all positive numbers, which is going to be positive. Sine of pi is 0, take away 1 is negative. Sine of pi is 0, plus 1 is positive. Only one negative there, so that will end up being negative. Sine of 11 pi over 6 is negative 1/2 times 2 minus 1. This is a negative number. This is a positive number, so that whole thing is going to be negative. So this means our second derivative is negative here, and negative here, and only positive here. So for concavity, it is concave up on the interval from pi over 6 to 5 pi over 6, and it is concave down everywhere else. And so that will be from 0 to pi over 6, union from 5 pi over 6 to 3 pi over 2, union also 3 pi over 2 to 2 pi. And these last two intervals can be combined because it does not change concavity there. So you have two inflection points, pi over 6 and 5 pi over 6. So f of pi over 6 is going to be cosine squared of pi over 6 minus 2 times the sine of pi over 6. And this is going to be radical 3 over 2 squared minus 2 times 1/2. And that is 3/4 take away 1, which is negative 1/4. And f of 5 pi over 6 is cosine squared of 5 pi over 6 minus 2 times the sine of 5 pi over 6. And this is negative radical 3 over 2 squared minus 2 times 1/2. And that is radical 3 over 2 minus, that is not radical 3 over 2, 3/4 minus 1, which is, again, negative 1/4. And so those points are your inflection points. And, yeah, that's a pretty challenging problem. You have to remember a lot of trigonometry to do this problem. And just for fun, here is the graph of that function. So decreasing, increasing, decreasing, local minimum, local maximum, and then from 0 to pi over 6, which is somewhere in here, it is concave down, and then there's a point somewhere right in here, that's your inflection point where it changes from concave down to concave up, and then it changes again from concave up to concave down, and it stays concave down for the rest of the problem. And that concludes this video lesson.